Hi guys, welcome to our lecture 12, and our topic here is going to be signaling, modulation, and multiplexing focused on wireless networks. So as you can see by the title, this is not a topic in which we will be focusing on the, the Wi-Fi technology itself, but some concepts that are required in order to understand how wireless and specifically Wi-Fi networks actually work. So this is kind of a more low-level topic, much more theoretical. Okay, so in order to understand how wireless networks work, actually any type of network, it can be wireless or wired, we need to understand signaling, modulation, and multiplexing. However, this is much more appealing when we focus on wireless networks because the performance of wireless networks are very much related to these subtopics. Okay, especially when we talk about power to signal to noise ratio or power to noise ratio, and we'll be focusing on signal to noise ratio before we can move forward to modulation and multiplexing. Okay, so as I mentioned, we have to understand a few concepts before we move forward. Initially, let's talk about these three concepts: entropy, redundancy, and noise. Most of the time, redundancy and noise are pretty straightforward. They're pretty easy to understand. Entropy is a concept that sometimes may get blurred, but it's also very easy to understand because basically entropy is the opposite of redundancy. So if you understand the concept of redundancy, you understand the concept of entropy since it's just the opposite of it. Okay, so entropy is the average amount of new information contained in each message received and is relatively unpredictable. Whereas redundancy is the part of the message that adds no new information to the message and it's relatively predictable. So as you can see, they're the opposite. Okay, so entropy is a message or data that is not known by the destination. Basically, that's new data. And it's very hard to predict the following data that is supposed to arrive to that destination. Whereas redundancy is something that is even repeating or it's easy to predict. And basically, redundancy is the concept that is used, for example, that is the concept that is used by compressing algorithms. So if you ever used any type of compressing tool, such as WinZip or RAR, or any of those compressing tools, file compressing tools, basically they rely on the idea of redundancy. If there are bits, for example, that are repeating, there are ways of trying to not repeat that data. So they're capable of removing data from the original information in order to reduce the amount of data that is supposed to be stored or transmitted. Same thing for data that is predictable. Maybe there is data that is not repeating, but the following data is predictable, such as in this example that we see here, we're ordering numbers from 1 to 10. Well, obviously, if I see a sequence 1, 2, 3, and then a few steps later I see 8, 9, 10, I can just assume that the numbers that are in between are 4, 5, 6, 7. Okay? And noise is unwanted modifications to the original signal. So noise is something that I don't want, right? It's similar to when you're listening to someone speaking and there are children playing around and even screaming um, right next to you. It's very difficult to understand the message that you're trying to understand because there is noise around you. The same thing happens for data transmission. So if we take a look at the Shannon communication model here, we can see that basically in a communication, we have the information source, as you can see right here. We have the transmitter, which is the device or the media that will be used to send the information to the receiver, which is also another device, for example, that will then forward that message to the destination. Now, there are situations in which the information source is the same as the transmitter, and the destination is the same device or person, for example, institution of a receiver. But there are situations that this transmitter is not the same as the information source, and the destination and the receiver is not the same as the destination. Okay, so for example, you are using your computer, which can be the information source, to send data to someone else, the destination. Okay, but you use your modem as a connectivity to the public network. That modem can be the transmitter, or even the network interface, the wireless network interface, for example, can act as a transmitter. Okay, now, in between, when the signal is being transmitted through any type of media, it can be wired media or a wireless media, some additional unwanted data can come in, which is called a noise, and it's being generated by a noise source. Okay, so the problem is, depending on how much noise you have, that noise may modify, may change the original message in such a way that the message that is received by the destination is not the same message as the information source actually sent. And that is a big problem. So there are techniques, and we'll talk about, we'll just mention these type of techniques that can be used in order to prevent that from happening, or in case that happens, it can even try to get to the original information, even though that information has been modified. Okay, in regards to wireless networks, they use a spectrum of a spectrum of frequency in which will be used to transmit data, because the data is being transmitted as a signal. So obviously there must exist a narrow spectrum in order to transmit that data, transmit those signals, transmit those waves. There are licensed frequency bands and there are unlicensed frequency bands. Now, licensed frequency bands are those bands that they are defined to be used by a specific type of source or a specific type of data. For example, military in the United States, for example, the military use a specific frequency band to communicate among themselves. So they have a licensed frequency band. There are the unlicensed frequencies that you can use to transmit data, transmit signals, and you don't have to pay in order to use that frequency. Actually, it's free for any type of device because they are unlicensed. The problem is there is a number of devices, a number of networks that will use those unlicensed frequencies because, well, it's free. Anybody can use it. So you can, for example, if you are a vendor and you manufacture wireless phones, cordless phones, well, you can reduce the cost of those devices, of those phones, if you use unlicensed frequency bands. Now, the problem is, as I mentioned, there are many different devices using the same frequency. The problem with that is that you're going to have interference, right? So once one device can interfere in the data that is being transmitted by other type of devices. So some examples of unlicensed frequencies, we have the 900 megahertz, which is used by UHF, cordless phones and stereos. And we have the ones, the standards, the frequencies, the spectrums that are known by Wi-Fi, the Wi-Fi standard, the wireless fidelity standard, which is the 2.4 gigahertz and 5 gigahertz. So, for example, 2.4 gigahertz, we have the cordless phones. So if you have a cordless phone in your house, that may affect your internet connection if you are connecting to the internet via a Wi-Fi network. Same thing for Bluetooth, NFC communication, and microwave ovens. So basically, this is the reason why if you have a device that supports 2.4 gigahertz and 5 gigahertz, you should try to use the 5 gigahertz technology because then you're going to have less interference. It is true that the 5 gigahertz network has a shorter reach, but at least you're not going to have too much interference when compared to 2.4 gigahertz. Two other concepts that are very important: understand the difference between bandwidth and throughput. So the bandwidth is the theoretical capacity of a channel, and don't only observe the theoretical word but also capacity, because it means whenever you mention bandwidth, that means you are mentioning the maximum theoretical capacity, which is different from the average. So the throughput is the amount of information that actually traverses a channel, and it's usually associated with the average. Now, another very important concept that we need to understand in order to understand how wireless networks work and how they perform is to understand the concept of signal to noise ratio. And it's actually these words are very self-explanatory because so you have the signal to noise ratio. That means that you have the power of a signal. Now, if the noise is too high, since it's a ratio, you have the signal, which is any number, and you have the noise. So signal is divided by the noise because it's a ratio. So that means that if the noise floor, if the base noise is high, then the signal to noise ratio will be lower. If you consider the same signal but with a lower noise, then the signal to noise ratio is going to be higher, right? So let me use a pen here. So as you can see here, right, this is a higher signal to noise ratio because the signal is right here. Actually, that's just the average. The actual signal is right here, okay? There. Now observe that the noise floor is down there, which means that the signal to noise ratio is going to be higher than this signal to noise ratio. And the reason is because the noise floor here is way too high. That means that the S and R will be a lot smaller, okay? And you always want to have a higher signal to noise ratio for a very obvious reason, right? The less noise that you have in your data, in the signal that is being transmitted, easier it will be to understand the original signal. If there is too much noise, the original signal will be so hardly changed that it will be very, very hard to tell apart what is noise, what is the original signal. Again, going back to the same example, if you are in an environment, if you're listening to someone and you are in an environment that there is some noise, but the noise is not too high, as we can see here, you can still understand what that other person is saying. But if it's such a noisy, if it's, oh geez, if it's such a noisy environment, as we can see here, it's going to be very, very difficult to understand the information that you're trying to understand. Now, it's very difficult to predict how much noise we're going to find in an environment that is not guided, it's not controlled. So wireless networks, they use the air to transmit data. And obviously, we cannot guarantee the how much and the type of noise that we're going to have in that type of environment because each environment has its own um, nuances. So obviously, we have to consider that there is a very high probability that we use the air to transmit data, but that air is going to be polluted by a lot of noise. That is a fair assumption, right? So in order to solve that problem, or at least mitigate that problem, um, modulation is a technique that can be used. And what is the idea of modulation? Is finding ways of transmitting data in such a way that if noise is incorporated to the original message, you can still, so you have a modified message, you can still get to the original message, okay? And if that's not the case, if we cannot implement a modulation technique that is capable of identifying that, this is what's going to happen, right? With a very high frequency, the destination will ask the source to retransmit that data, even though, as you can see here, in a situation where the message that was received is actually the original message, right? As we can see here. Now, these two, you can observe the signal over here. It's different from the signal over here, but in both situations, the message that was received was the original message. But since the signal has been so deeply modified, it's not reliable. So the destination may ask for a retransmission. Okay, now, a very simple way of implementing modulation is to create a coding table, such as this one that we can see here. Okay, so in this situation, we are using 11 digits. You can count the digits here. So we're using 11 digits to represent one digit. Okay, so for example, and this is a very common example, instead of transmitting, instead of transmitting C, we're going to transmit Charlie. Instead of transmitting C again, we're transmitting Charlie. Instead of transmitting B, we're transmitting Bravo. So forth, so on. And the idea is, so if I get this type of string right here, even though a noise is inserted into this string and it becomes, instead of Charlie, it becomes, let's say, something like this, another age here. Okay, we can still identify that the original message was a C. So that's the idea of modulation. Now, with the idea of modulation, we have a trade-off there, right? So the idea of modulation is to increase reliability, but obviously I have to transmit so many more bits, so much more data, that the transmission rate may go down. So there is that trade-off. The constant goal of modulation is to create a system that allows you to use modulation but without reducing performance too much. So we want to, in that trade-off, we want to have a positive ratio where the reliability is higher, proportionally higher than the performance degradation. Okay, so for example, in this type of modulation here, where we transmit 11 bits to correspond to actually just one bit, we had the first wireless, the first Wi-Fi standard, that we would transmit 11 million bits to have a transmission rate of 1 million bits per second. So it all evolved, other techniques, other modulations came up. So after that we had, for example, the DQ-PSK, differential quadrature phase shift keying, which actually doubled the performance. So we're still using 11 bits, but now to represent two actual bits, two data bits. Okay, so we started to being able to increase the transmission rate. Okay, so it evolved, the QPSK evolved itself, and allowing us to use the same number of chip bits, but now to transmit 5.5 megabits per second. Okay, and then 11 megabits per second. So we can see that we have this this possible solution, right? But still, modulation is something that can give us more reliability and degrade performance, but we're evolving in regards to performance degradation. But it was still not the best type of solution that we had, right? Now, another problem that, and so we're going to see that modulation combined with multiplexing can be an actual can deliver better performance. But for now, let's also take a look at the type of transmission, the way that wireless networks transmit data, right? So in the past, we talked about the current sense multiple access collision detection algorithm, which is implemented by cabled networks, specifically the Ethernet um, protocol, the Ethernet data link protocol implements CSMA CD. Now observe that it does use carrier sense multiple access, but it uses the collision detection algorithm. Now let's just quickly recap. The collision detection algorithm is basically an algorithm that will allow the nodes that are willing to transmit to sense the media, which is the wired media, to see if there is someone transmitting. If there isn't any other device transmitting, then that original device can transmit. But there is a possibility of, let's say, this device here, it senses the media, right? It senses the carrier and it says, okay, no one is transmitting, but this other one is doing that same thing. It's also sensing the carrier at the same time. So what happens is both of them think that there is no one else transmitting. They transmit at the same time. Now, the difference here is that since the Ethernet protocol implements collision detection, as soon as this collision happens, as we can see down here, down here, as soon as they detect that collision happened, they will wait for a specific time called backoff time. It's a random value multiplied by a very short period of time, milliseconds, 36 milliseconds, before it tries to retransmit, before it resenses the media and tries to retransmit. So observe that in a wired network, the devices can detect collision. And why can they do that? Well, because they are connected to that specific limited environment, transmission environment. So if there is something being transmitted there, they can sense, right? It's different from a wireless media. So they cannot implement collision detection. Therefore, they implement another algorithm called collision avoidance. And how does collision avoidance work? Okay, so let's take a look at this scenario. We have 1, 2, 3 devices, and they're communicating using a base station or a wireless access point here. Okay, but observe that the range of each of those devices cover the entire network. So this device right here has this range, right, which covers both of the other 2 devices. Okay, that's perfectly fine. And why is it perfectly fine? Because if this device here, if this device here is within the range of this other device, if there is a collision over here, this device can detect. This device can detect, right? Now, it's a problem in a situation such as this one, right? So if all nodes are within range of the access point, and they are, as we can see, but for example, node 1 and node 2 are not within range of another node, right? So for example, node 1 over here and node 2 are not within range of each other, right? So they are in range of the access point, but they are not in range of each other. So observe that this is the limit for node 1. This is the limit for node 2. So the limit node 2's limit does not reach node 1. Node 1's limit does not cover node 2, right? So if node 1 transmits at the same time as node 2, for example, none of these nodes will detect that collision. So the data will collide, right? Whatever this guy here transmits will collide with whatever number 2 here transmits, but they won't detect because they are out of reach, right? This problem is called the hidden node problem. That's why the collision detection algorithm doesn't work for wireless networks. Now, how does collision avoidance works? So since a node can never be sure that a hidden node exists because it cannot see the other nodes if they're out of range, but those nodes are within range of the wireless access point, then what they do is if a node wants to transmit, for example, node 1 wants to transmit, it will send a request to send to the wireless access point. The wireless access point communicates with all the other devices, right? So what happens is the wireless access point will be able to say, hey, yes, you can transmit because there is no one else transmitting. So it will send a clear to send message back to node 1, and then node 1 will know, oh, okay, so I can transmit, I can transmit, and then it transmits. So that's how wireless devices, specifically Wi-Fi devices, start a communication or a transfer. Now, as I previously mentioned, modulation is a very important technique used to increase reliability, but on the other hand, it reduces performance. Another technique that will help wireless networks to increase reliability, but also increase performance is it's a technique called multiplexing. Now, there are different ways, different multiplexing algorithms. In wireless networks, these are just a few, and I just want to associate them with the Wi-Fi standards that we know. But the idea of multiplexing is to find a way, to find a technique that will split the communication in such a way that will increase performance. For example, we have time division multiplexing, which was used by mobile technology maybe 15 years ago, I would say. And TDMA was that type, that is an example of a time division multiplexing. I think it was around 10 to 15 years ago. Now, other techniques, other multiplexing techniques came to life, and a technique that is very much used by wireless networks is the orthogonal frequency division multiplexing. So the idea of any type of FDM multiplexing technique, frequency division multiplexing, is that it will create subchannels of a frequency. So you have a higher, larger spectrum, and that spectrum will be divided, splitted into subchannels or subfrequencies. So We have FDM, the original frequency division multiplexing. We have orthogonal frequency division multiplexing. That is the technique that will actually create subchannels. As you can see here, you have subcarriers. We also had direct sequence spread spectrum. So many others, right? And nowadays, the wireless, specifically the Wi-Fi standards, they rely on OFDM. So as you can see here, we started with the DSSS, which was used by the B802.11 bit Wi-Fi technology. Then we evolved to the G and N standards using OFDM. Now, each channel has a width of 20 megahertz, right? And then we got to the .11n standard in the 5 gigahertz frequency. So observe that we have the N standard for both 2.4 gigahertz spectrum and the 5 gigahertz spectrum. So the 5 gigahertz spectrum will deliver a broader channel width. So that will give you higher performance. That will give you a more reliable channel. That will deliver a more reliable channel. But you have to remember that the reach is shorter, right? So again, try to use 802.11n standard if you're not way too far out from the wireless access point, if that's the case. And then you're gonna have a better performance. If that's not the case, if it's way too far, if you are way too far out from that concentrator, the access point concentrator, then you're gonna have to use the 2.4 gigahertz technology. Now, just to summarize, here is a table showing you the Wi-Fi standards that we have, the frequency division multiplexing that they use, and also the modulation schemes that they use. So you can see that there is a combination of techniques that are used to improve reliability and performance of Wi-Fi networks. So here are the standards, here are their frequencies and their speed. Now, another factor that will impact on the performance of your and the reach of your Wi-Fi or any wireless network is the type of antenna. Now, talking specifically about Wi-Fi, wireless fidelity networks, there are different types of antennas, but most commonly we're going to see the omnidirectional antennas, and that is the one that you see in commercial and residential access points, right? So if you have an access point in your house, this is the type of antenna that it's using, omnidirectional. So this is a top view. So this is the tip of the antenna. If you do a side, if you observe the side view, that is the antenna in the vertical position, and this is how it spreads the signal. Now, observe that mostly the signal is being sent in a horizontal direction. Obviously, it's not clearly horizontal. There is some diagonal transmission there, but not too much vertical transmission. But what matters is you're going to see that the signal is being irradiated, it's being emitted, it's being sent in all directions. So that's why it's called omnidirectional. That's the positive side. The downside is that the reach is short. So usually you're going to have a 100 meters reach in an open environment. So if you need to establish a communication between two very far, very distant devices, then the Yagi antenna will be, or the directional antenna will be the best solution, as you can see here. And there are different the manufacturers, the vendors, they create these antennas with a very considerable distance capacity. As you can see here, it's been illustrated by two separate buildings, geographically distant buildings, communicating using a Yagi antenna. Okay, now, when you use a Yagi antenna, there is still a Fresnel zone. So the signal is not precisely horizontal. There is kind of an elliptical signal being irradiated there, which means that this could happen, right? So although you're going to use what is called a line of sight to measure whether those antennas are going to communicate or not. So basically, when you are establishing that connection, deploying these antennas, you're going to do a line of sight analysis. So according to the line of sight, okay, these two antennas can communicate, right? Great, but that does not mean that the signal won't bump into somewhere which will cause, well, which can cause interference. Signal may arrive to the destination with some noise caused by that. It can also be blocked, and remember, it can be intercepted by someone over there. So there is still the need of implementing any type of security to guarantee that information is not altered or captured. Now, to finalize our topic, here are some topologies that you can deploy when you are deploying a wireless network in a wired network, which is usually the case. In very rare situations, you're going to have a fully wireless network. Usually you have a wireless network connected to a wired network. That is actually the core network. So one type of solution is each concentrator, such as switch, will have a access point connected to it. Each of those access points are independent. So they run their own DHCP server, their own network address translator. So each of these networks, the Wi-Fi devices here, the Wi-Fi devices here, they will be in an independent local area network, or if you prefer to call it wireless local area network. Another possibility is something similar, but the authentication will be implemented by a centralized authentication server. So DHCP and NAT are running independently, just the authentication process that is being taken care by that server. And you also have the more complex, more expensive, but obviously the better solution, safer solution, and easier to control solution, which is those access points are dumb. All the technology, all the intelligence is being implemented by these guys, mostly by the wireless controller. So the DHCP, the firewall, NAT, authentication is all running here. You can also separate some services such as what you see here. But what matters here is the most important concept that you have to visualize is that these devices, oh geez, these devices are dumb. They're just forwarding the packets that are being sent by the node or that are being sent to that node. All the technology, all the intelligence is forwarded to that guy and implemented by that guy. So in this class, we discussed some concepts that are very important in order to understand how wireless, specifically Wi-Fi networks, work. I hope you enjoyed this class. Thank you guys.